Hello everyone. Am I audible to you? All of you? Please, anyone just confirm me by
Yes,
writing in
ma'am.
chat. Okay, thank you. Good evening, everyone.
Ma'am,
Yes.
ma'am, I got an email that the Tuesday's class that was to be held on 7th of March is going to held today from 6 to 8 in another link. How we are going to do that?
No, this is like there are two TA in this course. So one is of my session and another is of some another person called named Soda Bhadra. His classes. So you may join either of them, either me or him. It doesn't matter.
Okay, ma'am. Ma'am, either Saturday or either Tuesday, any
Yes.
one day.
Yes.
Okay, ma'am. Thank you.
Okay. Sure. Okay, in the due time, people are joining. Let them join. But now I will start and welcome back again to the course. This is a week 2, session 2 discussion. Okay, people are joining. Let me add them. Okay, so let me start that. Welcome back to the second session of our discussion in the NPTEL course of Nuclear Astrophysics. Today, I am your TA Nilaksha Shanapati, and we have problem solving and doubt clearing classes every Saturday, 5 p.m. to 7 p.m. So today we are going to discuss about many topics, actually many important topics. But before that, let me give you before that, let me give you a tour that what is covered in the course in week 2. Week 2, in week 2, professor has discussed about evidence of nucleosynthesis 3 and mass gas, then the HR diagram, then ML relation, Hubble's law and echo of Big Bang, then the thermonuclear reactions and reaction cross section, and a detailed analysis of reaction rate. The now we will discuss about many important thing in today class, and we will obviously solve a few questions which will be helpful for your examination and as well as to learn this course much more deeply. So we will this is the Google Meet link again given here, and that is already shared with you by Swam portal, now by which you are going to join this class. And the few things are that if anybody is new here today, then I would like to inform you that if somebody miss any classes, then please visit to the YouTube channel link, and there you will get the there you will get the these lectures, these classes, these sessions any time, and you can see in the YouTube. Because if you miss or if you want to check again, then please visit that. And I am not sharing that link again. If anybody has a link at this moment, then please share that to share that, you can share that in the chat box, or otherwise I will share in some within some time the YouTube channel link. And please, someone is sharing his screen. I think, who is that person? Please stop sharing. Who is this? This is, I think, Yuva Shri. Are you sharing your screen? Please, if anyone is sharing your screen, then please don't share it. Okay, somebody is asking for the link of the class. Okay, let me share it. Wait 5 minutes, then I will share it. This is the link of the channel, and previous for previous class. Wait a minute. Um, this is the link of the YouTube link of the previous class. So you please go through that. It will be helpful if you have missed somehow it. So let me start now today's class. Okay, all right. So let me start now today's class. So these are the things that that professor has covered in the week 2, but there are lots of topics that we will discuss today, and these are the main things that we are going to learn today. And today is a very important class, because we are going to cover a huge amount of thing and lots of discussion today. And the second thing is that from the previous week class, we discussed that some of the topic you wanted to discuss again, and some of in some details. So for that I will start discussing those topic first, and then I will move to the questions and accordingly one by another. So what are the key concepts to learn today? Let me tell you in very brief manner that first we will cover luminosity. What is luminosity? Because we are talking lots about luminosity, and this is one of the very important thing to learn. Then the with that we will go to the apparent and absolute magnitude with the in the continuation of the luminosity, and then we will further move to the HR diagram. These three topics will be covered in a single shot, we and within the continuation of each other. So these three topic covering a huge part of this course, and it will be very helpful for your examination purpose also, because HR diagram and luminosity are two things. I am sure that you are going to get some question from there. Now, then the astronomical distances, we have discussed that we have some sort of we wanted to discuss it again. You guys have told me that it will be very helpful if we discuss the astronomical distance again. So I will discuss that today in very brief manner, but not in the continuation of that. But at last, I will discuss about astronomical distances, and in between that, the week 2 thing which has covered by professor, and I will discuss newly, that is the velocity distribution and the Maxwell Boltzmann distribution, plasma, and some of you, I have seen that in a ask a question portal, they you have some of you have some question that that why we are using Maxwell Boltzmann. You will get to know that here. Then we will solve some numerical MCQ of thermal energy, velocity distribution, all those. Then we will calculate Q value. We will we'll get some understanding again on the on the AMU, that is atomic mass unit, and conversion into the joule into the mega electron volt, and all those things. Those are very primary things which you need to know, so it will help you to boost your confidence and to get good score in the examination, because that those small things are the main things which actually make it which actually give you trouble during the examination. Then I will go to the life cycle of stars, and then a short revision if time permit. And I have also seen that some of you have raised question in the ask a question portal, that what is quantum tunneling. I think those who have already done his or her BSc, who have completed, then they must have some knowledge of quantum tunneling, and those who are masters, obviously they have knowledge of quantum tunneling. But this course is for everyone, so I will discuss quantum tunneling a bit, as some of you some person of among you have requested for this. And then two things I have shown here, that is a liquid drop model and a cell model, which are written in the light color, because I wanted to ask you, I want to ask you that if you that professor has discussed told you many times that go through this liquid drum model and cell model once again to revisit this, but many of you have covered it in BSc third year, or some of you may or may not have covered it till now. So I would like to ask you at the last that should we discuss liquid drop model and cell model once again in this discussion session? Then if and last but not the least, modeling of a star. Modeling of a star, that professor has mentioned about this, but in the lecture there is no modeling, it is not discussed in in a elaborative manner. So if you guys are if you guys are interested to learn a modeling of a star, that how we do this, and what are the equations that we what are the partial differential equation that we solve, then I will definitely show show you guys that in the next class. But that is a later half of the of today's discussion, that I will that will be an interactive session, while where I will discuss about discuss with you about those things, and accordingly I decide that what to do. Okay, so now let me uh, go to the go to my writing pad, and there I'll start today's discussion session. And in between this class, if anyone have any question, then please feel free to write into the chat box or unmute yourself and ask question. Okay, and there is always the ask a question portal where you can always ask a question. So that is the thing. Now who have joined newly, please for them see these topics at the new topics that we are going to discuss today. That is what I was discussing in this first few minutes. So now I will discuss about now I will go to the writing pad and start our discussion. At any point, if you find that if you are unable to see you are unable to see any tab or the writing pad or the slide, then please let me know that. In this time I will stop sharing the this thing, and please, now I am going to write it in the writing pad. Okay, 1 minute. So is this writing notebook is visible to all of you?
Yeah, visible to me.
Okay, so let us start our discussion by asking the question that what is luminosity.
Ma'am,
Yes.
how do ma'am
Sorry, I can't
on
hear you.
my how doing assignment, ma'am?
How?
How doing assignment, ma'am?
The assignment that is already shared with you, the assignment 1, assignment 2, assignment 3, assignment 4 is also shared yesterday for you in the swam portal. You please sign in the swam portal, and you will get the week 1 assignment, week 2 assignment, and you have to solve them. And week 1 the topic, the questions which are covered in week 1, that we are going to, that we have already discussed now, which is covered in week 2 and related to the week 3, that we are going to cover today, that is
Okay,
the
ma'am.
week 3, and so on.
Right,
Yes,
right, ma'am.
your voice is actually breaking. Please tell again. Whoever is asking something, please tell again. I am unable to hear you, or either write into the chat box. So I don't know what was her exact question, but if anybody has any doubt about assignments, then the assignments are there in the SWAM portal. You just have to submit those assignment there, and whatever questions we are discussing in this discussion session, these are extra questions, or some of the questions are from the assignments which we are which we are discussing for the final examination purpose. and obviously you need to submit the assignments within the due time, otherwise you will not be able to get write the examination, the final examination. At least you have to submit 6 assignment among the 8 assignments to get the chance to write the final examination. Okay, so okay, now let's start the discussion that what is luminosity. So first let us consider, when we consider a star, then we consider that a star is a point source. This is our assumption. On the basis of that, we this is obviously not an ideal case, but whenever we do something theoretically in preliminary level, we do some assumptions to to understand it easily, or to get the vibes that what it is actually happening there in some simplistic manner. Otherwise it will be very complicated. So if we consider that this is the star, this is the star, and it is a point like source, and here we are in the earth. Then we are getting the spectrum, we are getting the light from the star, we are getting the light from the star, which is actually the information that we have. And any information, any light, that is electromagnetic wave, nothing but the electromagnetic wave. So what we can calculate is luminosity directly from this, and this luminosity now then what is the definition of the luminosity? Then we can define the luminosity as how much energy is radiated isotropically per unit time interval. That is the luminosity. And what is the specific luminosity? Specific luminosity is the yes.
Ma'am, when applied exam last date, ma'am.
Sorry, the registration for the last date of the registration.
Yes, ma'am.
Last date of the registration is 17th March, uh, uh, 2023. 17th March 2023 is the last date of the exam registration, uh, up to 5 p.m. and examination. Yes,
Fees, ma'am. Fees, ma'am.
I think I did not exactly remember, but it is I think 1,000.
Okay, ma'am. Thank you, ma'am.
Okay. Please, if anyone have any doubt, regularly visit the SWAM portal. There is almost everything which you need to know. Okay. All right. So we are discussing about the luminosity. Luminosity is how much energy is radiated isotropically per unit time interval. Let me write it for your. To
Hello, ma'am.
yes.
Ma'am, there will be another session today from 6 to 8 p.m.
Yes, the thing is that there are two TAs, two live session will that is going to conducted for this course. One is of with me, and another with some another TA. So
Okay.
so you can join either one of them.
Okay, but that means that two sessions the content will be the
Same.
same.
Same means the questions which will be solved, that will be more or less same. That will be same.
Okay.
But it depends upon the TA also, that which are the extra topic he or she is covering.
Okay. Okay.
Okay.
Okay.
Okay.
Okay.
So
Thank you.
then we can write the definition that what is the luminosity? Luminosity is how much energy is radiated isotropically. This is important because we are considering a point like source, and it is radiating isotropically. Like there is nothing like absorption, scattering. There is nothing like some in some direction it is more or less. We are not considering any of those cases right now. We are considering very simplistic case, and by that way, and it is actually, it is, though it is an ideal case, but for far away distance, the stars are very far away from us, so this case is way more realistic case that we can consider. So it is not that we are, no, as it is ideal case, so we are not going to deal with this, but this is not like that. We are going to deal with this only, but there is the assumption that stars are like point source. Okay, so now the definition is how much energy is radiated isotropically per unit time interval. Now if you, this is a luminosity. Now anything that is specific, like specific luminosity or specific flux density, then what is that? Specific luminosity is just luminosity in a given frequency range. Okay, so the anything that in examination or in any MCQ, any question, if asked about specific, then you must have to remember that we have to find it out within some specific frequency interval. Then how will we write luminosity? Luminosity is L, that is equal to del E by del T. That is the mathematics. Del E is the energy radiated by the energy radiated isotropically by the star, and del T is the time interval. And what is the specific luminosity? That is, I am denoting with the L nu, that is equal to del E by del T into del nu. So this is a specific luminosity. This you have to find out the luminosity within a specific frequency interval that will be told to you. So these are the things that which is the definition of the luminosity and the mathematical definition of the luminosity and specific luminosity. Now one more important thing is there, that is specific flux. That is like there is star, it is radiating isotropically again, and we are on earth seeing it with telescope. Okay, now daily is the energy radiated by the star, energy, and del T is the time interval, del nu is the frequency interval. All right, that is why we are telling that how much energy is radiated isotropically per unit time, per unit interval, per interval, that is a specific luminosity. Now the thing is, luminosity is that quantity which is actually directly telling us about the star's energy itself. So, and in case of specific flux, like what I am discussing right, what I am discussing right now, that the star is emitting light. It has some energy. Now some amount of it is falling into our telescope, and we can see. Now the radiation. Then what is the specific flux? The specific flux is the radiation falling in the detector normally means perpendicularly, per unit time, per unit area, per unit frequency. Obviously we need to consider here the area, because there is some specific area of this telescope, right? We are not we are not or this is coming from a part, though we are considering that this is a point like object, and we are considering that point like object is isotropically radiating. But when we are seeing through a telescope, then there is some area, not we are seeing that from the whole of it, so their area comes into the play. So the what is specific flux becomes is that the energy that is falling on the detector, let me denote it with the del E 0 by del T, del nu, del A. This is the flux, specific flux. Now specific flux is a new quantity for this course, because this is not introduced till now, but I am introducing this specific flux here to get because I want to discuss HR diagram thoroughly, and there and also want to discuss about the apparent magnitude and absolute magnitude, which terms has been coined in the lectures also, and such that you get the idea of the apparent magnitude and absolute magnitude as well as HR diagram very neat and cleanly. Okay, Sumit is raising his hand. If anything you want to ask, please write into the chat box, and I will see and I will definitely answer. Otherwise, you can unmute also. So now the thing is, we know the specific.
I had a question.
Yes.
Okay. So what is the difference between delta E and delta E naught? Are they the same quantities?
Delta E and delta E naught.
Yes.
Delta
For luminosity,
E
we
is
use
the
delta E.
delta E, which I have defined firstly. That is the energy. That is the energy that is radiated by the star, and delta E naught, that is the energy that we are detecting by our detector. They are not
Okay.
same, right?
Yeah, they're not same. Correct.
Okay. So but yes, but delta E naught and delta E is connected like delta E naught by delta A is equal to delta E. So from that part, from that thing, we can actually connect luminosity and specific luminosity and specific flux. And the relation which we will finally reach, I am not going to discuss all the steps here, because that it can be done very easily by you also, that how we are reaching to the relation. But this is the relation that we will reach, and if anyone wants, then I may discuss, but it will take some time, and I have to discuss a lot of things today. But this is the now what let us understand that what this relation actually tells. This is a specific class. This is the luminosity. Anything I am writing new in the suffix, that means it is specific. Okay. And the S is the distance between the star and the detector or the earth. I mean, here if we consider the star and earth system, then this is the star, this is the earth, radiating isotropically, and there is this earth. This is the if we consider the total area, then it should be like all over these, right? But we are observing from a particular part. That's why we are considering the delta A thing, which is now considered in case of specific class. If it is coming, then the distance, if the distance between these two is s, then the relation what we will get is this relation. This highlighted thing, that is the f nu is equal to L nu by 4 pi s square. This is an important relation. S means I will later have I may write S as d also. This is just the distance. Okay. So this is a very important relation that you need to keep in mind, such to understand the further topic also. Okay. So this is the first part that we have discussed today. What is luminosity? Luminosity is how much energy is radiated isotropically per unit time interval from the star's perspective. Now, and the specific luminosity is the luminosity in a given frequency range. Now, if it is specific flux, then the radiation falling in the detector normally per unit time, per unit area, per unit frequency. That is the specific flux. And the relation between luminosity and specific flux is f nu is equal to L nu by 4 pi s square, where f is the distance between the star and the earth system, and the distance between the observer and the object. Okay. So this is the first part. Now the second part where we are going to relate these things and know about one another quantity, that is what we call the magnitude, and then we will relate these things with the HR diagram. Now the magnitude, sorry, if anyone is asking any question then please ask, otherwise please mute yourself. Magnitude we are defining with m, that is equal to a alpha log 10f plus c, where alpha is some scaling factor, f is the flux, c is defined, c is like let me write it here, it is defined by a reference star which considered to be brightness 0. Like this is, please someone mic is unmuted, or please mute yourself. Okay, so and I don't know whose mic is on, please unmute yourself. Okay, so C is a constant which is defined by a reference star which considered to be brightness 0. And brightness 0 means that is one that is the most closest star, one of the most closest star, and about which star we have enough knowledge and very accurate knowledge, and we consider that as a reference point of us. With respect to that, we observe any other star or unknown star or far distant star, and that which star we consider as a reference star, mostly we consider Vega as our reference star. Okay, so this is a relation. Now if you ask me that how we are getting the magnitude, like why we are writing it in this form, magnitude is nothing but another logarithmic here the log scale plays a very important role in case of astronomy, in case of astronomical things, because these are the very long distance, short distance which you need to we can't actually plot or get the exact idea. We what we do is everything we generally plot the logarithm log plot, that is a logarithmic plot, and the logarithmic thing actually, if anything here in the astronomical is 10 to the power something something, it depends upon in that manner. So when we get any logarithmic scale, then we have the idea of the scaling factor differently, and the exact value of the quantity differently. That's why it is important to get the idea or define anything in the logarithmic scale. And this logarithm here, this magnitude, that is just another form of flux itself, was defined by Hipparchus, and this we called the Hipparchus magnitude, which is defined as m equal to alpha logarithmic 10 f plus c. And these things you can note it at this moment, it is as a definition of the magnitude. Okay, so if now we know what is the magnitude. Now another important thing is that we generally talk about bolometric magnitude, or bolometric, something called bolometric. What is that? Bolometric magnitude means anything which we call bolometric, that means it is integrated over all lambda, like any star or anything that is emitting in the in the total EM wavelength range that I was already discussing in the previous class. It is not like it is emitting in a 600 nanometer only, or 300 nanometer, or some millimeter or sub millimeter or gamma. It is always emitting in the all the in total electromagnetic spectrum range. And when we consider about the magnitude which is integrated over all lambda, that is we call the bolometric magnitude, and we can write it as m suffix lambda, that is equal to 2.5 logarithmic f lambda, that is the that is also like integrated over all, plus c lambda. This is the bolometric magnitude. So first thing was magnitude. Let me sorry. Okay, first thing is magnitude, that is defined as like this, and second thing is this is the bolometric magnitude. That is defined like this. Okay, magnitude and volumetric magnitude. Now we can write this m lambda, sorry, we can write this m lambda as minus 2.5 log, in terms we can write this in terms of specific luminosity now, that is 4 pi d square. D is nothing but the a's, that is a distance. So c lambda. So now it is I think very clear that how I am writing this, because I have already defined that this is the equation 1. Equation 1, that is the f nu is equal to n nu by 4 pi a square or l nu by 4 pi d square, anything you can write. D means distance. And the second thing was this, this is the equation number 2, that is the magnitude m equal to alpha logarithmic of f plus c. Now I am defining volumetric magnitude, which is m lambda equal minus 2.5 log f lambda plus c lambda. Now finally we reach another thing, that is the volumetric magnitude in terms of specific luminosity, and this is important. Equation 3 and equation 4. So how this factor 2.5 comes, that like the scaling factor, that is if you do in a whole range, or how we are actually calculating this thing, that I am not discussing here, but you can consider it as a constant here, 2.5, because how this alpha scaling, see, first of all, when Hipparchus discussed about this magnitude, it was it was not like something derivation, it was something like some intuition or some idea that it can vary like this. It was a trial and error method, and it was a notion that maybe it can vary like this. Now 2.5 is the constant, that is in further research it was discussed, and it was invented that we can do the scaling with the 2.5. And finally what we use right now at this moment of the magnitude is minus 2.5 logarithmic l lambda by 4 pi d square plus c lambda. Now exactly how it is coming, that is out of this course, and you don't need to very much bother about this thing right now. Okay, so that is a thing which is the absolute volumetric magnitude in terms of specific luminosity. Now we will define another thing, that is the absolute magnitude. That is I am defining as capital M lambda is equal to minus 2.5 log 10 L lambda by 4 pi 10 parsec square. What does that mean? First, magnitude was just that, how it is varying with the f lambda. Now how it is varying with the luminosity at any distance, that is the original distance d between the star and the object, and the star between the object and the observer, that is a d. Now I am writing d as 10 parsec. It means that if any star that is at any distance d, but we are considering that suppose that star is at 10 parsec distance. If it at 10 parsec distance, then what will be the magnitude? That is what we call the absolute magnitude. No matters what distance it is, but this is, if this is at 10 parsec distance, then what will be the magnitude? That is the absolute magnitude. But this is not the real magnitude of the star, because all stars are not in 10 parsec distance, right? We are considering that if d is 10 parsec, then what will be the magnitude, and that is we define as absolute magnitude. And you may ask that why we are considering that star is at 10 parsec, and why do we need to define such a quantity. And you will understand that in when I will discuss further that why it is necessary. Because whenever we are knowing an unknown star which is not known to us, and we want to know that, then we don't have really many understanding of that star, about the distance and all those things. But we have the understanding of the luminosity, and once we have the understanding of luminosity and magnitude, and if we do some ratio, then what we will get is d, that is the distance. We will be able to calculate that. So previous time I solved a problem where I showed you that using Hubble constant we can get the idea that in how much distance the galaxy is, or the star is, or the any astronomical object is. Now this is another technique where you will be able to get idea, or you will be able to calculate the distance of the object, of the astronomical object, very finitely. And this is this is one of the very accurate, uh, uh, very well established method to calculate the distance also. And why? Because this is related to the HR diagram also, and how we will reach to the HR diagram, that I will discuss now. But before that, I am showing you that why this absolute magnitude is important. Because now see that it is absolute magnitude is m lambda. Now let me subtract volumetric magnitude, that is small m lambda, from the capital M lambda. Then what we will get is 2.5 log 10 L lambda by 4 pi 10 parsec square by L lambda by 4 pi d square. 4 pi will be cut out. So now what we will leave left with, that is that is the L lambda by 10 parsec square by L lambda by d square, that is equal to m lambda by m lambda. Now why m lambda minus m lambda is important, I will not discuss. There comes the role of the photometry, which is a very popular technique. Whenever we have discovered or seen some star, we generally do two things. One is photometry, and another is spectroscopy. These are the foremost important thing to understand a star in its preliminary stage. And from these two techniques, we understand many things. So whatever I am discussing at this moment, this is the basic of the photometry. Okay, so by the m lambda m lambda minus m lambda, that is there are many UV, BV, this kind of photometry technique that is not part of this course. That will be a little more for this course. So I will not discuss those things. But remember these things, that this is the basic of the photometry, and we need we need absolute magnitude and the volumetric magnitude to get the idea of the distance of a star from us. And this is a very helpful technique. So now and you can understand that once we have the idea of the luminosity, then we can get the idea of the magnitude also. Once we have the idea of magnitude, we can have the idea of the absolute magnitude as well as the distance. So these are all related. I hope now you can relate by yourself also that how one by one thing is coming. Okay. So this was the second part. Now I will directly move to the most important thing, that is the HR diagram. So the next thing, that is the third thing, I have denoted it like that. Like any star, we consider it as a black body. First thing is that we are talking so many things about luminosity. We are relating luminosity with the distance, with the flux density, with the magnitude. That means we need to know the luminosity, or that is the most important or foremost important thing that we need to discuss. Then how will we get the luminosity also? Then comes the role of black body radiation. We considered that the stars are emitting like a black body. So we can write the L but equal to 4 pi sigma r square t to the power 4, which is Stefan Boltzmann law. And I hope whoever have idea about the black body radiation, all of them have idea of this equation also. But if anyone does not have the idea of this equation, then please tell me by unmuting yourself or by writing in the chat box that you don't know it. If you don't know it, then I will discuss it in very short manner in next class or sometime in between the discussion. But I am currently at this moment, as most of you are BSc or MSc student, I think that most of you are aware about this. Chinmay is writing that she does not know about this. Okay, that's all right. At this moment, you take it as a point that stars, we consider stars emits like black body, and we have some Stefan Boltzmann law. If you know the black body radiation thing, then the it directly proportional with the t to the power 4. And how it is if we calculate all the things, that what we get is L equal to 4 pi sigma r square t to the power 4, where sigma is the Stefan Boltzmann constant. So this is very important thing actually. And for Chinmay, I will suggest that please go through the black body radiation once, and if you have any problem, please write into the ask a question portal. Otherwise, write into the chat box, or as you are telling it, then I will discuss about the black body radiation in very brief manner in next class or at the last of this class. But let's see when we can discuss. Okay, but I will definitely discuss. Please continue the session. Okay. Okay, so that is the this is the basic equation. Now we have the idea that how luminosity will vary with the temperature. So if we take the logarithm log in the if we take the log in both sides, and also we take the sun scale, length scale, like I have previously discussed in the previous class, that whenever I will write this signature, that means it is telling about sun. L sun, that is the luminosity of sun, is equal to 4 pi sigma r sun square r sun square t suns to the power 4. Okay, like this. So at this moment, if we if we consider that r by r star, if we just want to see that could we get of this class copy, since I joined sometime later today. Okay, sure, I will share this with you. Actually, I share all the notes and all the slides with the NPTEL. I don't know if it is shared with you guys or not, but definitely I can share it with you. You can write your mail, whoever wants this class
Yes,
note.
ma'am.
Please write your mail ID here. Then I can maybe directly send to you, or maybe you can ping me in the mail ID. I will directly share it with you.
Your mail ID?
Hmm. Okay, this is my mail ID. You can ping me there by writing that you are a registered student of NPTEL this course. I will share the note with you if it is not shared with you already.
Okay.
I generally share these all these things with the NPTEL portal, but I don't have exactly the idea that if it is already shared with you or not. Okay, so whoever want, please write me in the mail ID. I have already shared it in the chat box.
Okay, ma'am.
Okay, so this is the so if we consider that other things are constant, though radius is not constant. Some of you may ask that radius is not constant, obviously, but just as we are looking for the relation between luminosity and the temperature, so for this time let us consider that 4 pi sigma r square, that is if we take the logarithmic, those part is just a constant, then how it will vary? It will vary just 4 log t by t sub. So this is a one very important thing. Now we will understand why. Because in HR diagram, what we want to know, what we do, we actually get the relation between the luminosity and the temperature. One hand, in another hand, we also connect that with the magnitude, and we all that is already that we can also relate that once we have the idea of the luminosity, then we can connect it with the magnitude. That's why another thing is magnitude, and the last but not the thing, not the least, another the fourth thing is spectral time. So what now we have relation between the luminosity and temperature. Once we have that, we also have the relation between magnitude and luminosity and temperature. And as we have this magnitude, again it is used to define the spectral type of the or spectral class of the stars also. So we can directly relate it with the spectral class of the stars. So at the end, what we can do, we can relate luminosity, temperature, magnitude, spectral class all in a single thing, and that is nothing but the HR diagram. Okay, so finally we reach to the mathematical understanding that how we are getting the HR diagram. So let me go through that, and then I will relate it with the mass also. First thing is that we know about the luminosity. Luminosity is the energy per unit time interval per unit frequency interval. Then one, we know the specific flux, that is that is the radiation getting detected by the detector per unit time interval per unit frequency interval per unit area. Then what we get is the specific flux, that is the then we can write it. Then we can relate it with the magnitude. It is called the Hipparchus magnitude because it was defined by him, and that is m is equal to alpha log f. F can be directly related with the luminosity. L nu is that is L lambda by 4 pi d square. And once we have the idea, then we can relate the magnitude with the luminosity and the distance. We have defined absolute magnitude. Once we have idea of absolute magnitude and volumetric magnitude, we can find out the distance of the object with the observer. And we there are two important things, and this is the basic understanding of the photometry also. We can do that using these basic things. We actually do the photometry, though we are not discussing photometry and spectroscopy here. That is not the part of this course. And next, what we are discussing is that we consider the stars emits in black body, like black body, and it behaves like this manner: L equal to 4 pi sigma r square to the 4. If we take the logarithmic scale and consider that though other parameters are not varying, 4 pi sigma is obviously constant. And if we consider r is also not, r will obviously vary. But if I want to see the relation between luminosity and temperature only, then log L by L sun is equal to c plus 4 log t by t sun. Now where now as we are leaving the r radius part, then what we need to do? We obviously need to consider it because it is also a variable. So radius is obviously is depending with the volume. That means we can say it vice versa manner, that volume is dependent with the radius. Once the volume is dependent on the radius, and we know the volume is equal to rho is equal to mass by volume. So once this volume is related with the radius, that means mass is also related with the radius. And other thing, like rho is equal to m by v, and if m is, that means m is equal to rho into v is equal to 4 by 3 pi r cube, something like that. We don't know how it is varying. Now at this moment we can tell that we can't tell that we consider that star as spherical thing, but we can't say that it will vary, but it is not exactly spherical. We all know that our sun or anything, even earth also, it is not exactly spherical. And how it is varying, that is depending upon the radius, that is as it is depending upon the volume. So so luminosity is also somehow related with the mass. And as we have also seen that luminosity is depending upon the radius, and radius is dependent upon the volume is dependent upon the mass. That means luminosity is dependent upon the mass, but how, that we don't know. So now we can write that L by L star, that is equal to m by m star, m sun, sorry, to the power nu is some constant here now. Okay, so this is some power. We don't know that what is the power, that how the luminosity is varying with it. Okay, so if we take the logarithmic, then L by L star, L by L sun, that is equal to nu log m by m sun. So somebody was asking in the ask a portal question, ask a question portal also, that how that he or he know about the Stephen Boltzmann equation of black body radiation, and it always vary with the t to the power 4, and it will vary with the r square. Then how we can write that something to the we have written something r to the power 3.5 and some other things, some things we have written, right? So I exactly did not remember what was there in the lecture, but it was written there, and somebody asked that how we can write that, because we don't know that how the mass is actually exactly varying with the luminosity. And for that purpose we write it with any nu, and we actually take the data of the luminosity and the mass, and we check that what power law it is exactly following. Once we know the power law, what power law it is following, we know the in logarithmic scale, we know the nu from the slope of the graph. And once we know the slope, that is the nu, this is nothing but the slope in the logarithmic scale, and that will go in up if we remove the logarithmic scale. And then we will get that how for this kind of stars, mass will vary with the luminosity with this power scale. This kind of stars will vary with mass and luminosity with this power scale. That is how we get the relation between luminosity and the mass. So this is the basic thing, that these are the basic things of HR diagram. Now I will show that whatever I have told to you by now mathematically, how we are plotting that in HR diagram. When you will see the HR diagram, you will very easily get the you will very easily understand that why we plot luminosity versus surface temperature versus magnitude versus spectral class in HR diagram. And I hope by now I am already clear that in HR diagram how we are relating all these four terms. All right. So before going to that, let me ask one question to understand that whatever I am telling is that clear or not. Suppose this is a question 1, that star, this is a question 0 maybe, like no question. Star A and star B have the same radius, but star B is twice as hot. Twice as hot. Hot means you can understand that this is somewhat related to the temperature, obviously. So, how much more luminous is star B? Answer this question. This is a very simple question, very simple with a one line, maybe not even one line. You can solve it. Just you need to tell that which star is more luminous and by what factor. Everyone please try. The question is star A and star B have the same radius, but star B is twice as hot. How much more luminous is star B?
16 times.
2 to the power 4.
Yes. Yes, it is absolutely correct. 16 times. L proportional to t to the power 4. That means that means t to the power 4 means 2 to the power 4. That means 16 times. As it is proportional, then it is 16 times. So B star B is 16 times more luminous. So now let me stop sharing this and go to the slides.
Ma'am,
Yes.
I have a question regarding the assignment which is already submitted and
Yes.
I got a 4.
Hmm.
One mistake I have done in yesterday in previous assignment, that is the in HR diagram the metal which is the poor, I think what is the poor or yes, which is the poor metallicity. Actually the metallicity which is the HR diagram in the left portion, the temperature is more high than metallicity is increasing. But my question is that, according to my thought, why between the white dwarf and just form bonding, just monster, between these two, why the just monster metallicity is very much higher than, because metallicity defined as two types of two in kind of two way, that is the how much content of hydrogen and helium at the stellar object, and other way the fraction of ferrous and hydrogen actually. So my question is
FD
that,
by H.
my question is that, no, in white dwarf and and the new forming star, new burning star, who which is more metallicity or which is less metallicity, and why? My question is regarding that.
Okay, so what in assignment one or two, I don't know. You have some question regarding this, right?
Yes, ma'am.
So what was the exact question? Can you tell me? Otherwise, I'll not be able to understand that if there is some mistake or not, or whatever you are telling, that is absolutely true. Let me clear that your thoughts are absolutely correct. You are not wrong. So to get into the right direction, I need to have the question with me.
Ma'am,
Otherwise,
I can share the screen.
okay, okay, you just share it, share.
Yes, ma'am. This is the assignment 2,
Okay.
and this is the red mark and the yellow mark, A and D. The one question is that, uh, which one has the lowest metallicity? My answer is white dwarf, according to my thought, but the answer would be A, that is new burning star.
Which one is
This is
A and
the-
which one is D? That okay, the red one is A and the yellow one is D.
Yes, ma'am.
Okay, and but the thing is that here absolute magnitude and what is given in the right side of the HR diagram. Can you slide
Yes,
it?
ma'am.
That is the luminosity. Okay,
Yes, ma'am.
so luminosity is lower that means it is okay, and temperature is lower, uh, and temperature there, the magnitude is higher, luminosity is higher. So the thing is that why the metallicity of A is higher than the metallicity of B? This is your question, right?
No, no. My question is which is poor metallicity and why?
Okay. So obviously, okay, which is poor metallicity? The answer will be A. Obviously, the poor metallicity is A.
But why?
Because okay, as your let
Could
me
I stop this then?
yes, you can stop. Okay, now let me tell that that when the white dwarf is the last stage of a life cycle of a star, right?
Yes, ma'am.
That means it has already exhausted all its energy, and
Oh,
it has reached to the highest binding energy level, that is the Fe level. That's why it become the white dwarf.
yes.
So if you calculate the Fe by H, that means high metallicity will be for that white dwarf. That means poor metallicity, that Fe by H will be lesser for the A. That is the the upper corner thing. That's why the poor metallicity is A.
Okay, ma'am. Okay, ma'am. I got it. I got it. Because the in white dwarf the all hydrogen fuel that is gone.
Yes,
That's why
yes.
the high. Okay, ma'am. Okay, ma'am. Thank you,
Okay.
ma'am. I
Okay.
got it. I got it.
Very nice. I forgot what was your name, Ambarish. I think he was asking some question. Please feel everyone feel free to discuss like this. It will be helpful for you also. Okay. So now let me share my screen. I think you can see the slides. Can you see the slides?
Yes, it is there.
Okay. So as you can see the slides, now let me go to the HR diagram. So this is the HR diagram, that is here it is just plotted at L by L sun with the M by M sun in the log scale. And this is what I was discussing, that we will have some power of the some power that is with which the luminosity and the mass is dependent upon. And if you plot a scatter plot and then fit with the power law, then you will get that within the -1 to 0.2 something like that, it will vary like with delta 1.38 slope, then the slope will be 3.95, then it will be 5.45. This is how the trend has been observed with the observational data. Okay, and this is how we tell that with the observation we know that for which kind of stars how the mass is varying with the luminosity. So this is the one thing that I have just discussed right now before this question discussion, that how the luminosity and mass will vary. This is the plot of that, and this right side plot is showing the HR diagram, which I have just discussed for 1 hour right now, that how the luminosity will vary with the absolute magnitude, with the temperature, with the spectral class. Here you can see that both the y-axis are shown with absolute magnitude and the luminosity with respect to sun luminosity, and this is the spectral class. There are seven spectral class of the stars, and this is the surface temperature in Kelvin. So if you see that if we plot it in a scattered plot, then you will get this kind of plot, and this line is actually the main sequence line, and sun also fall in main sequence line, and where the one is given, this if you plot a straight line here, then where it will go, there you will find that our sun is there. With respect to sun, we measure all of the things in terms of luminosity. So there are supergiants, and there are white dwarfs. That means when after becoming a main sequence star, first it will start now it has lots of fuel, lots of hydrogen. That is why it is in main sequence. That is why if as it is more towards this upper corner, that means it has more hydrogen, that means more luminous. And as it will pass is in its life, then it will be red giants, red supergiants, and it will move towards this direction. That means the temperature will also increase. Okay, so first a main sequence star will go to the this part, that is the supergiants, and red giants or red supergiants, and then it will come back to this part when it will lose all of its fuel, and now it is metallicity is increased and it is more towards Fe, the binding energy is highest, then what it will reach is white dwarf stage. So this is from this HR diagram, if you know what is the luminosity of a star, that is what primarily is calculated, then you know what is absolute magnitude, what may be the temperature, what may be its state, what is the spectral class. So that is why this is so important diagram in astronomy, in case of stellar evolution, in case of stellar astrophysics, in case of nuclear astrophysics, and any domain of astrophysics where we deal with stars. And if you now when we I will use the writing pad again, I will say that how that whatever I am telling, that first it will start its main sequence, then it will go to the supergiants or red giants, and then it will end up its journey with the white dwarfs. So its cycle is like that, and you can relate it with that. The luminosity is increasing, then it is going to the radiation, so temperature is increasing, then it is coming to this direction, temperature is again decreasing, and it is becoming an O type star, and absolute magnitude and luminosity both are decreasing. So once you have idea of one quantity, you can get the idea of other quantity. And as well as if anybody tell any question about HR diagram, you should have the notion that by knowing the HR diagram, I can interpret something about the star. That is what you need to learn from this course. And I hope by now I have discussed a lot of things and lot of stuff, lot of mathematics uh, for this HR diagram, and this is now clear to all of you. And someone is asking that, can you please explain what is spectral class? Spectral class is like we categorize the stars in some spectral classes, and those are as written M, K, G, F, A, B, O. And right now, if you and how this is done, that is another thing that should be discussed in some details. But at this moment, I am not discussing about the spectral class, but it can be as it is going towards from the red giants to the white dwarf things, it becomes M2O. And if you ask that what is sun at this moment, our sun is right now G type star. Okay, so spectral class I am not going to discuss at this moment. Now let us solve some question. A lot of discussion has already been done, and we need to solve some question, right? So first question. Question 1. It is telling the velocity distribution of the particles in the stellar plasma has a maximum at which velocity. Like you need to tell the which velocity at which velocity the distribution of the particles of the stellar plasma will be maximum. So let me share my this screen, the writing pad. So question 1 is telling the velocity
1.3 keV.
How you get the value? I did not give you any temperature or anything. Okay, are you talking about the second question? I am right now at this moment at first question. Then I will discuss about the second question. And at this moment, if you want to try for the second question, you can try. And I will whoever has answered, I will obviously show the second question and discuss that if he is right or not. Okay, so now the question is the velocity distribution of the particle in the stellar plasma has a maximum maximum velocity at which. So you have option, right, like root over 3 kbt by m, b root over 2 kbt by m, c root over 8 kbt by 3m, d root over 3 kbt by 2m, and so on. So there are more options. So can anybody have any idea? Do anybody have any idea that what I am trying to tell with the velocity distribution of the particle in the stellar plasma here?
Actually, in the stellar, my thought is that behind this, the velocity of plasma can be studied through in two way. In one is kinetic theory approach and one is fluid dynamics approach. And in this kinetic theory approach, we can just expression the velocity Maxwell velocity distribution expression, the maximize the term, and we can get the answer. We could be get the
Absolutely,
answer.
you are absolutely correct. We are here with that kinetic theory term. We will do that. Whatever who was who are you? I forgot the name, but yes, you whoever has still. What is your name?
Ambarish.
Ambaris, yes. Ambaris is absolutely correct that the process is like that. And in short, if you want to understand that, that will be nothing but the most probable velocity of the Maxwell Boltzmann distribution, because we are going to do the maximize things and all those stuff. And if we do the thing, what we will get is the root over 2 kbt by m. But if you do this manner, like half mv square is equal to kbt, then you will get the v is equal to nothing but root 2 kbt by m. But I want to this is a very simple question, but to why I gave this question is because somebody has asked that that why you are using Maxwell Boltzmann distribution here. This is coming from the Maxwell Boltzmann, right? We use distribution because when we consider plasma, stellar plasma, what is stellar plasma? First ask this question. What is plasma? Plasma is a collection of the positive and negative particles that follow the quasi-neutrality and collectiveness property at the same time. And what does that mean? What does that mean? That means we have lots of positive particles and we have negative particles. But in case of plasma, that is the fourth state of matter, there within this radius, that we can see that I am not quantitatively correct in this picture, but what you can get the idea that how many the number of positive and negative charge will be equal, and within this radius, which is called the Debye length, within this radius it will behave as a collective manner, and it will behave like a neutral property, like a neutral matter. Like there are positive charges as well as negative charges, but within that Debye length it is behaving like a neutral because there are equal amount of positive and negative charges, and plasma has that property that it will behave in a collective manner, and it will within the Debye length it will not within a certain radius it will behave like a quasi-neutral. It will show its quasi-neutral nature. That is what is the scientific definition of plasma. So as it is neutral, finally as it is neutral in nature, and the density of the, like this is a blob of this is a blob within the Debye length, and there are, like if it is a plasma distribution, then there will be something plasma quasi-neutral property with the some length here also. And if we consider the density of that matter, that is not so high, and temperature that is not so high, that is a low particle density, and the temperature is quite high, and that is the condition where we use the Maxwell Boltzmann or the classical statistical distribution. That's why we can use Maxwell Boltzmann distribution in case of plasma. Okay, and in thermal equilibrium, obviously in thermal equilibrium. So so if you say that what is the definition of the plasma, then let me write it in a very fast manner, because there are lots of things to discussion. Plasma is the collection of positive and negative particles that follows the quasi neutrality and collectiveness property, and collectiveness property. This is the definition, and there are two things to remember. That is, one thing is uh, yes, for this collective behavior. No, this is called the fourth state of matter, and it is not like either liquid, not like either solid, not like the other three matter, the other three things. It is absolutely different things. Neither liquid, neither not solid, or this or gas. This does not show any collective nature, collectiveness. Obviously, that is true. That is the one point that you have mentioned. And the second thing is quasi neutrality also. These both of these properties are the uniqueness of the plasma. And these are if somebody asks you what is plasma, then in the definition the quasi neutrality condition and the collectiveness property, these should be mentioned. Then it is like a scientific definition. And with that collectiveness property, we can talk about the temporal domain of the temporal distribution of the plasma. And with the quasi neutrality, we can talk about the spatial distribution. And from the temporal, actually we get the plasma oscillation. These are some to know about this, I can I can do a single class on this plasma and on the properties of these, but this is not a plasma discussion. So just to introduce plasma, just to have an idea what is plasma, that's why I am just writing this. If anybody finds anything, then please unmute and ask, or write into the chat box, or in ask a question portal, anywhere. But this is not a right place or right time to discuss much details about this. And but I am mentioning these things, that within the Debye length, within the Debye length it is plus and minus. Once you go to the out of the Debye length area, then it is quasi neutral. Totally it behaves like a neutral matter, that it is neither have positive charge nor have negative charge. And if you do the collectiveness property, then in temporal domain it has some plasma oscillation, which varies with the which varies as root over n, where n is the density, particle density. So this is the fundamental things, but at this moment you don't need to what is happening. At this moment you don't need to go through all these details. Just remember that plasma is this, and this is the fourth state of matter, and in the thermal equilibrium it follows the Maxwell Boltzmann distribution. So now let me go to the uh, mm, question thing. Maybe okay. Let me go to the questions. Share. Share now. Okay, let me go to the question. The next question, that is the second question. Can you see the tab? Can you see the slides? I hope you can see the slide. And the next question is question 2. Question 2. That is what somebody was answering about, that at the sun's core, that is T equal to 15 megakelvin, the associated thermal energy is, the options are given. I am not writing the options. 0.13 mega electron volt, 1.3 kilo electron volt, 0.3 mega electron volt, 0.1 kilo electron volt, 13 kilo electron volt, 0.3 kilo electron volt. Whoever has answered me, can you please tell me that how you solve the problem? This is a very easy problem. Or anybody, those who have not solved, please try to solve by yourself. Ishariya S, please stop the screen. Stop your screen sharing. Ishwarya S, please stop your screen sharing.
It's 1.3 kilo electron volt.
Yes, how you calculated that?
E is equal to kT.
Yes, this is exactly what it is. E is equal to kBT. E is equal to kBT. That is how you need to solve. That is, please, whoever has shared his or her screen, mobile screen, please stop it. kBT is equal to 1.3 keV. Now the next thing is that now the next question is question 3. Question 3 Question 3 is it is telling that a star with mass 10 times that of the sun consumes its nuclear fuel faster by what factor? A star with mass 10 times that of the sun consumes its nuclear fuel faster by what factor? You guys try to solve it, then I will discuss. By that time, let me share the screen. Okay. So the question 3 is telling a star with mass 10 times that of the sun consumes,
Ma'am, 1,000 times, ma'am.
how you calculate? Yes, please discuss with your friends and me. Faster by what factor? A 10, B 100, C 1000, D 10,000, E1000000. So how to calculate? Okay, let me discuss that the nuclear energy stored in a star is proportional with its mass. Okay, and the time over which nuclear burning occurs, that is equal to star's lifetime. Yes, L is proportional to m to the power 3.5 minus 3.5. M is proportional to 10 to the power 5. Yes, that is also a process that you can directly do, and otherwise I can write that tau is equal to tau is equal to En by L, and that is equal to m to the power, and L, that is m, for the nuclear energy in a star, it is direct mass is directly proportional with the m, and over by the time the star's lifetime, it is for a given time, for a given star which has mass less than the 10 solar mass. For those kind of stars, luminosity is directly proportional with the m to the power 4, so it is about m to the power minus 3. So if you do that, 1 by tau, you can directly do by m to the power 3.5, or it is another process. You can directly do, you can calculate that 1 by tau, that is equal to that 10 times, that is equal to the answer that it will give you 10 to the power 3, that is about 1000. Okay, so a star with mass 10 times that of the sun consumes 1000 its nuclear fuel faster, 1000 times faster. Okay, so this was the third question, and I think I am not explaining much more about these things again, because I can see that people can answer these things, and that is very good, and I am very happy for that. And so that's why I am not discussing much more about this question anymore, because I don't have much time also for today's class. And I will go to next question, that is question 4. And before going to the question 4, if I have some other plan, I think, okay, yes, before going to the question 4, there as it will be on Q value, so I will give a short discussion on Q. We will discuss some Q value in very short and very fast. Okay, so Q value we have already the in lecture also it is discussed in lecture 9 in great detail, but I will not go through those things. Rather, I will discuss the conversion of the units. That is very important for the examination purpose, because most of the cases there students make some mistake in the conversion of the units. Okay, so that's why I will discuss that. But delta mn equal to m, what was that, m nuclear minus z mp minus n mn, it is equal to mass defect. I am not writing. Delta E is equal to delta Mn c square, that is equal to binding energy. Very important thing in nuclear astrophysics, in nuclear physics, and in everything. Binding energy is very important concept. And if there is some reaction, nuclear reaction, from where 1 is going to 3 and 4, then what will be the Q value? Q value will be Mn1. For nuclear, it will be Mn1, Mn2, for Mn3 minus Mn4, and for atomic, QA is equal to Ma1 plus Ma2 minus Ma3 minus Ma4. Okay, so this is already done in the class, but how to change the how to calculate the units? How to calculate the units? First is AMU, that is the atomic mass unit. what is the definition on it? It is, the definition is 112. Sorry. Okay. 1/12 of the mass of the atom of carbon 12C isotope, C12 isotope, taken to be exactly 12 units. That is symbolized by U, that is called the atomic mass unit, and it is written as 1 U. It is calculated as 1 U is equal to 112 into 12 into 10 to the power minus 3. The exact unit is 12 unit by 6.023 into 10 to the power 23 kg. That is equal to 1.660566 into 10 to the power minus 27 kg. If you want to convert it into the joule, then you have to do 1.660566 into 10 to the power minus 27 c square joule is equal to, if you want to do it into the into the electron volt, then 166 into 10 to the power minus 27 c square by 1.6 into 10 to the power minus 19. I think these values you are aware about, that 1.6 into 10 to the power minus 19 what it is, so I am not describing these things. So this is electron volt, then now you will get 931.502 into 10 to the power 6 electron volt, that is equal to 931.502 mega electron volt. Okay, so this is the one U. How to calculate the first thing is how to calculate 1 U to kg, then 1 U to joule, then we are as mass is equivalent with the energy, so we can directly move to energy, and that is what it is showing, that we are converting the mass into the energy directly by multiplying with the c square. That is why what we know equal to mc square, nothing else. And then we are getting the joule, then we are dividing with the 1.6, and we are getting that how it is varying with the how it is in electron volt, and finally we are getting it into the mega electron volt region. Okay, now we can calculate it in case of mass of electron. Mass of electron is what? 9.11 into 10 to the power minus 31 kg. That is equal to 5.48 into 10 to the power minus 4 U. And once you know the U, then you can calculate by multiplying with the 931.502. You can know about the mega electron volt, that is energy. Then MP, mass of proton, that is 1.677265 into 10 to the power minus 27 kg. We all know that will be equal to 1.0072765 U. Now next thing is Mn, that is equal to 1.67495 into 10 to the power minus 27 kg is equal to 1.0086650 U. Okay, so these are the value. You can note these are the very important for the examination purpose, because this kind of transformation makes trouble in examination. Now if I tell that what is the binding energy, mc, m not it is c, not it is not c, it is me, m electron, mass of electron. Mn means mass of neutron, mp means mass of proton. All right, mass of electron, mass of proton, and mass of neutron. These things in U is very important to calculate the binding energy. Now for example, I will calculate binding energy of alpha particle. that is 2He4 to practice. For the practice purpose I am doing this. Okay. So what do we need to do? First we need to calculate ZMP. ZMP, that is equal to 2. Z is equal to 2 for 2He4 into 1.007275 is equal to what it is, 2.014553 U. Z into Mn, that is equal to 2 into 1.008665 is equal to 2.01733 U. So if you add these two, then what will you get? 4.03183 U. And what is the mass, atomic mass of 2He4 that will be provided to you? This you have to calculate. This will be provided to you. What is the actual thing? Then that if you do the subtraction between them, then what we will get is 0.02928 U. That is equal to into and if you multiply that with the 931.5 MeV, then you will get 27.27 MeV. So this is the binding energy of the 2He4, that is the alpha particle. So this is the process. What will be provided to you? You sometimes these things are also provided, but sometimes it is not provided. So better you remember these things. And 931.5 conversion. This is very must thing that you need to remember. And this will be provided, obviously this will always be provided to you, that what is the exact thing from which you have to subtract. And then once you have this thing, then you can calculate that what is the binding energy in terms of electron volt, or you can convert in joule or whatever you want, because now you know the conversion. I have shown that how to convert all these things. Okay. So this is the next thing. Now let me go to the stop sharing this and go to the question maybe. Now you should be able to calculate the next question. Stop sharing. Can you see my slides?
Yes, ma'am.
Okay. So the thing is, the question is, calculate the Q value of the reaction 3He plus 3He plus it is converting to 4He plus 2P, and aim of 4He, that is a mass of that is given, mass of proton is also given in Mu, and mass of 3 helium is also given. Everything is given to you actually. Now calculate the Q value and you have the options. Everybody please try it. Now you should be able to you should be able to follow the previous discussion, whatever that I have just done, and you should calculate it. I am giving you 2 minutes. Please calculate it, and then if everybody is all right, then I will go to the next question, and in short I will discuss this. Please try to solve it. Are you trying? Okay, so this is the Q value. Everything is given to you. This is the mass of 3 mass of 3 that is given to you in there. And from the equation, you have to do this and this. This is corresponding to M3He. And somebody is telling that option D, yes, if Nived Nivu, and he is absolutely correct. The option D is correct thing. Then the 4He is this thing, M4He. And now next is 2P, that is also given, that is 2MP. Sorry, 2MP. This is the color coding. This is the M3He and this is the M4He. So you have the all of the things. Now just calculate it and put all the values. Everything is given in AMU and it is directly converting into the 2 MeV. Sorry, into the 931 into 5, multiplying with that, you are directly getting the MEP region. So you will be finally, if you calculate it, let me do the calculation also. I think the steps are like 3.016 plus 3.016 minus 4.0026 plus 2 into 1.00727 and multiply, and this is AMU, and multiplying with 931.5 MeV, you will get to the MeV region. And that is how you are getting. Let me not do the step jump here. 0.01486 into 931.5 MeV, that is equal to 13.842 MeV. Alright, this is the question 4. Now let's move to question 5. I think everybody has understood that this question 4. Which of the following is unstable? So somebody has raised some question. We don't need to multiply Z. Where is Z? Okay, so no. Here the thing is that mass of 3He itself is given. That time I was calculating binding energy. For that I was again dividing with subtracting with that. I was calculating all those things. This is just want to calculate Q value, and Q value is nothing but these things. This is the Q value. The difference between the mass of the nucleus of the 1 2 minus mass of n 3 and 4. This is just the Q value. Okay, don't like don't manipulate with between these two things. This is the thing, and I hope that it is clear to you now. And this is the Q value. This is the Q value. This is the Q value. I have discussed with all the conversion of the units, and now we have I have also talked about the binding energy, and now we have calculated the Q value, and now we are going to solve the question 5. And this is a very short question. Which of the following is unstable? Which of the following is unstable? Option A, diproton. Option B, neutron. This question is just an informative question. Di, neutron, all of them. Which of the following is unstable? So the answer will be all of them. These all of these things, diproton, neutron, dineutron, these are all unstable. All right. Now the next question, question 6 is find one minute. Find luminosity of a star whose radius is 696,340 kilometer and surface temperature is 5778 Kelvin. Options are 3.85 into 10 to the power 33 R per second. Option B 1.92 into 10 to the power 33 hours per second. Option C 2.46 into 10 to the power 31 hours per second. Option D 1.92 into 10 to the power 31 hours per second. So these are the options, and this is the question, that find luminosity of a star whose radius is 696,340 kilometer and surface temperature is 5778 Kelvin. Then what will be the luminosity? And I have discussed 1 hour with this luminosity, magnitude and all those things today. So, and I think the relation between luminosity, radius and surface temperature is very much clear with you, as I have mentioned about the black body thing, that we consider the star as a emitting like a black body. So I hope you can relate that with which just one equation, you have everything. You just have to calculate the luminosity. Radius is given to you, surface temperature is given to you. Please everyone try it. I am writing the hint. Somebody is telling it will be C. Godhuli is telling it will be C. Okay. I don't know what equation you followed, Godhuli?
L equal to 4 pi Stephen's constant r square t to the power 4.
Yes, you are right, but maybe somehow you have you have done some mistake in the calculation. But yes, that is what you need to calculate, and I think you can calculate that, everyone. That is just the calculation mistake, I think, but you have absolutely catch it correctly. Yes, Nibu is saying it is A, and the answer is actually A. And Godhuli, please check your calculation. You just have some calculation mistake, that's all. Otherwise, you have absolutely catch it correctly. Balusa is also saying A, and it is A. All right, it is A. And I am writing. Then let me write for the other peoples also. 4 pi, and I think everyone can solve it. I can see by your response, everyone can do this. And then 4 pi r square 5.67 into 10 to the power minus 5 args okay, the 4 s to the minus 2 into 10 to the 4 is 5778 Kelvin to the power 4, that is equal to 3.85 into 10 to the power 33 args per second. Very simple question, but very important question. This kind of question you will get in the examination. You can expect this kind of question. Now another informative question. This is taught into the class, actually into the lecture. It was there. That's why I have put that everybody is watching the lectures as well. which of the let me go to the slide. You can pin to the slide that the question is, which of the following processes is responsible for the production of elements having mass number A, where 28 A is between 28 to 60. And this was covered in, I think, lecture 8 or 9, lecture 8, like 6 or 8, yes, lecture 8. Which of the following processes is responsible for the production of elements having A between 28 to 60. And options, I am not writing. The options are carbon burning, oxygen burning, neon burning, silicon burning, SRT process or L process. Anybody has answered? And I think somebody has answered. Ma'am, are we allowed to carry calculator in exam hall? I think no, you are not allowed, and they will provide you calculator in the computer screen. That is what actually happened in the any national examination, and I think in case of this also it will happen. So, and is there any negative marking? I don't think so. In case of this examination, I don't think that if there is negative marking, so there will not be any negative marking. And though I am not 100% confirmed, but I think there will not be any negative marking. And calculator they will provide by you in your exam into the computer screen. But in the examination day you can carry your calculator. If the permits, then you can take it with you, but I think it will not be allowed. And the answer is D, silicon burning. Yes, you guys are right, it is silicon burning. Now let me go to the everybody pin the the slides. I will directly read the slides and go to the question 8, question 9 and question 10, because I don't have enough time today. Already time is passing, but 1 minute. Yes, already time is passing, but yes, I will try to finish this question 8, 9, 10 first, and then as today we wanted to discuss few more things, but maybe it will I will not discuss it today, because today already it is 7. But let me go through the question 8, question 9 and question 10. Question 8 is saying that what is the anticipated future of the sun. The A is option A is energy production will stop after hydrogen burning, as the sun is not massive enough to burn helium. Option B is sun will become a red giant during the helium burning phase. Option C is sun will ultimately collapse into a black hole. D, it's impossible to predict the future of the sun. And the answer is B, sun will become a red giant during the helium burning phase. And who has answered? Somebody has answered again. Balusa has answered. Godhuli has answered. Yes, both of you are right. Correct. Question 9 is saying that please, whoever have not answered or not getting it, either write to me and share the question to you, or please take a snapshot of the screen and remember this type of question. This will be helpful for your examination, and or you can write it. And the question 9 is telling protons in the sun can be described using Maxwell Boltzmann distribution due to. I have already answered this question. What will be the answer? Somebody wants to tell anything? Otherwise, what is the answer? I have already answered this question during the discussion. Godhuli is saying 9B. Manisha is saying 9B. Yes, you guys are absolutely correct that protons in the sun can be described using Maxwell Boltzmann distribution due to high temperature and low density.
Ma'am, I have a question.
Yes.
I have studied that Maxwell Boltzmann distribution cannot be applied in case of protons and any other subatomic particles.
Okay.
Then how it can be applied here?
No, this is not we are not talking about that subatomic domain or quantum mechanics, anything like that. We are not talking about quantum mechanical thing here. Here we are talking about bunch of proton. Like what is there are bunch of proton in the sun, inside the sun, and they are particle. They are just particle. They are random particle. What we consider, there is a box and there are random particles. Here there are protons and sun is a box. There are random protons. And due to the high temperature and low density, what are these particles will follow? What this particle will follow? These particles, whatever they are there, the protons, they are also, the sun is there, the plasma is there only. And we know that quasi neutrality and collectiveness will be followed there, as I have already discussed in the class today. So it will always follow the Maxwell Boltzmann distribution. But if you consider a particular point at 10 to the power minus 8 angstrom level, it will never follow Maxwell Boltzmann distribution. It will follow FD or BE. But here we are considering these are like particles and not very high dense, rather very low dense and high temperature. That means they have the space to move around. They have they have it is more like elastic collision because they are not colliding with each other. Those kind of situation are there. That's why we can consider this as a classical distribution of randomly moving high low dense lots of particles. That's why we can consider it is Maxwell Boltzmann distribution. And this is the cause, and I hope it is clear. But don't make a misconception that proton follows Maxwell Boltzmann distribution. No, that is not true. You are right that in quantum mechanically it will follow the FD statistics obviously. But here the comparison, whatever the protons are moving in the sun, the situation is creating like that. That's why we are getting the we can consider the classical distribution, that is Maxwell Boltzmann.
Okay. Thank you.
Okay, and Santosh Kumar is saying that, ma'am, is the session will be uploaded in YouTube? Yes, it will be uploaded in YouTube. I will try to upload it within today, but within tomorrow it will be definitely be uploaded. Please, if you want to get the you can give a reminder or what is that called, that YouTube red button, some bell ring button is there, which you can do that and subscribe, that you will get the notification whenever I will be uploaded. Or it will be uploaded for sure. Now I wanted to discuss with you the astronomical unit also, but I think today time will not permit us. Which of last question? Let me go through the last question. That which of the following cannot be described using the Maxwell Boltzmann distribution? Now this is the question for whoever was talking lastly with me regarding the Maxwell Boltzmann. You try
Yes,
to
ma'am.
answer. You try to answer this. That which of the following cannot be described using the Maxwell Boltzmann distribution? Now think, the previous question was when we can use high temperature and low particle density. Now it is telling which of the following cannot be described using Maxwell Boltzmann distribution: the sun, main sequence star, red giant star, supergiant star, white dwarf. And why? You try to answer it. The condition you remembered that for Maxwell Boltzmann it is high temperature and low particle density. That means if there is low temperature and high particle density, then Maxwell Boltzmann distribution will not be followed. And for
It will
which
be
of
white
these?
dwarfs.
Yes, that will be the answer, that white dwarfs cannot be described using the Maxwell Boltzmann distribution because they have high density and low temperature. So that is this question two one by one question I have given because of that understanding that this is situation dependent. It does not mean that FD or BE is will not be applying, or quantum mechanics not true. No, absolutely, those are absolutely true. But this is the situation that letting us consider the Maxwell Boltzmann distribution. All right.
Yes, ma'am.
Okay. So I now I'll stop sharing. I'll just go to the slides, and let me tell that what I wanted to discuss today is first thing luminosity, HR diagram, apparent and absolute magnitude. I have discussed those things. Velocity distribution I have discussed. I have discussed plasma, thermal energy, Q value, but I am unable to cover life cycle of star, quantum tunneling, astronomical distances, and this portion. So, are you guys energized enough till now to continue with the astronomical distance, life cycle stars, quantum tunneling, all those things, or should I discuss these things in next class?
Then we can continue.
I can continue. Okay, and then I will. And one more thing, first of all, let me ask that liquid drop model and cell model. Everybody knows about these two things.
Can you please describe the shell model?
Monisha is saying yes, and I want to know about what is the response of the class that liquid drop model and cell model. Do I need to visit once to these two topics in next class, or I should not? Do you guys want that I revisit the liquid drop model and cell model once or not? So everybody knows about liquid drop model, and yeah, ma'am, kindly teach these models. Okay, so yeah, quick revision is okay. Okay, so I will do a quick revision on next class, liquid drop model and cell model, and modeling of a star. That is a huge topic, and obviously I'll tell that in next class. But quickly, I will do the life cycle of stars and and try to do astronomical distance today. Quantum tunneling is also some process, and somebody has asked that, so I need to tell that in some sort of detailed manner. So I will not discuss that today. So let me go to life cycle of star very fast. So life cycle of star is nothing but it is known to all. It is formed by stellar nebula, and there are two kind of star that is mostly generated. Either it is a average star or it is a massive star. Average star is within the 10 solar mass, and a massive star is greater than 10 solar mass. We call that massive star. Those which are average star, they go to the red giant mode in their next stage, and then after the red giant mode, when it starts to go the more energy is now lost. There is less amount of fuel inside the star. So the pressure between pressure inside pressure, the gravitational pull, and the Fermi pressure that is directing towards outside, that fight again starts to fight against each other. Like inside pool of gravitational collapse and outside pool of Fermi pressure energy. So within that fight, Fermi pressure, when Fermi pressure wins and it is force is toward the outward direction, then it get blast and form into a planetary nebula. And if it is a red supergiant for massive star, then it will blast into a supernova, and it is more luminous and much more energized rather than the planetary nebula. And for the red giants, it forms the planetary nebula, and for red supergiant, it forms a supernova. Now, this planetary nebula will form the white dwarf. Then it will form the white dwarf, means the part which will be left at the end stage of the star, that is, it will remain as a white dwarf. That is a low luminous, high metallicity, and O spectral type, and it will be low temperature, low luminous. Yes, and other than that, for the red supergiant, it is become supernova. Then it falls into neutron star, either neutron star, and if it is very high massive, about 100 solar mass or more than that, then it becomes black hole. So there are three kind of last stage of star. Either it becomes white dwarf, it is or neutron star or black hole. And in case of our sun, by now we know that it will become a white dwarf. For neutron star also there are pulsar, which pulses a one category is pulsar, and pulsar pulse emits this pulse from the both end point, both pole points, and there are millisecond pulsar, there are black widow millisecond pulsar, there are red bag millisecond pulsar, there are various category of these pulsars. And if you call about black hole, there are various category of that also. People have tried categories it, but black hole is black hole, not that is another domain of studying the astronomy. Black hole astronomy, pulsar astronomy is another domain. There is whole lot of study with the neutron star and pulsar, and these neutron star or pulsars are very appropriate probe of the universe. With it we can do many things. We can even nowadays, with the help of these pulsars, we actually want to detect the gravitational wave also. And the white dwarfs are the last stage, and these are not so useful as a probe of the universe. But these neutron star and black hole, these obviously are very hot topic and very emerging topic at this point of time. So this is the life cycle of a star. It starts from a stellar nebula and it ends up with a white dwarf, either neutron star or black hole. And now the thing is, I will just write that astronomical units. uh, um, Quick revision is okay. So that is, I think, for the liquid drop and liquid drop model, and uh, um, liquid drop model and the cell model. All right, that I will cover up in next class. Modeling of star next class, quantum mechanics, quantum tunneling next class, and astronomical distance. Maybe I can. It will be very fast if I do today. But yes, there are three astronomical units, three main distance, astronomical distance. One is astronomical unit, or 1 AU. Second is light year, and third is 1 parsec. Astronomical unit is distance between Earth and Sun, roughly. Light year is distance light travels in 1 Julian year. You can go through what is Julian year by yourself, but right now I can write it as 365.25 days. That means that 6 hours extra, that is also considered here also. And Julian years is a European year calculational thing which we use in astronomical purposes mostly. Julian year is very important, but that is not necessary to discuss at this moment. And 1 parsec is what I am showing into this slide. That is this is 1 AU, that is the Earth and Sun distance, and this is the angle which sustained 1 arc second. And this distance, then this base is called 1 parsec. That means the distance which subtends 1 arc second with the 1 astronomical units in that triangular basis, the base is the distance which is called the 1 parsec. You try to understand this thing, this picture, take a snapshot or whatever by searching. I think this picture is very clear that what do you exactly mean by the 1 parsec. And further than that distance, we consider is some parsec, some 3 parsec, 2 parsec. We calculate with respect to this parsec thing. Okay, and there are relations like 1 AU is equal to 4.848 into 10 to the power minus 26 parsec. 1 light year is equal to 63241 AU. You can convert it into the parsec also now. 1 parsec equal to 3.26 light year is equal to 2.06265 into 10 to the power 5 AU. Okay, so this is the main funda, but I will stop here today because there are less people now, and it is already 2.5 hours. So this is the main thing. I think that this some idea you have got about distance, but I will start discussing about I'll start next class from the discussion of this astronomical distance itself. Okay. So today what we have learned a lot of things today. First of all, we have discussed a lots of things about luminosity, HR diagram, apparent and absolute magnitude, then velocity distribution, Maxwell Boltzmann distribution, what is plasma, thermal energy, Q value, life cycle of star, astronomical distances, all those topics. And is not tomorrow, in the next class we'll start with the some astronomical distance again, then some liquid drum model, cell model division, quantum tunneling I'll go, modeling a star. I'll do some quick. I'll try to do a quick give a quick glimpse of modeling of a star. That will be very useful and helpful. And then we will go with the next classes problems and some new topics and some revision. Okay, so I hope today's session was helpful enough and you have all enjoyed, and I am very happy that you guys are trying to solve the questions and discussing. And please feel free to ask question in a ask a question portal, and also try to keep in contact. Whoever wants to get the notes, please write, you can write to me in the my mail ID. And thank you for joining, and surely we are enjoying the classes and we will enjoy. See you again. Okay, bye.